start. So thank you very much to Barbara De Marco, who accepted to be our invited speaker today. She's, just to give you a brief introduction of her, she had a PhD in CISA in Trieste. Then she went for several postdocs around in Bologna, at Max Planck in Munich, in Madrid, in the CAB, in the SIC. And then she has been in the Copernicus Astronomical Center in Warsaw with several fellowships, in particular a Marie Curie fellowship. And since a few years ago, she's Ramon y Cajal fellow here in Barcelona in the Universitat Politécnica de Catalunya. So welcome, Barbara, and we are very keen to listen to your talk on accreting black holes and on prospect on Athena. Just go ahead. I will give you the 5 minutes.
Okay, okay. So thank you very much. Thanks for inviting me to give this talk. So today I plan to discuss one of the scientific objectives of Athena, which is the study of the innermost region of accreting black holes using spectral timing techniques. Now, by innermost region, we are referring to the region where most of the gravitational energy is released, which corresponds to a region of around tens of Rg from the black hole. Now, these regions, of course, are very small in the sky, so the only way to study them for most of the objects that we know is to use methods that are other than images. Okay, so before going into the details of these techniques, it is important to ask ourselves, why are we interested to look so close to the black hole? Now, this question has an obvious answer for most of you, but it is important to, anyway, to highlight this answer. So basically, we know that black holes are important bricks in our universe. They contribute in shaping the universe as we know, as we see it. So in order to reply to important questions like, for example, how do black holes grow? How do they influence the universe? How do make feedback to pass information into galactic scales? So we need to understand how they work on nuclear scales. Okay, so let's give a look at these nuclear scales. And so now these nuclear scales in some sense are quite messy. We observe a lot of phenomena coming from these inner regions. So first of all, we have accretion. Accretion, as we know, is the main engine that produces these enormous amounts of energy. Then we have the effects of the black hole, so the strong gravity effects due to the vicinity of the black hole. So this makes the regions ideal laboratory to test general relativity, but also we can use these effects, these relativistic effects, to measure the parameters of the black holes, in particular the black hole spin. And then these inner regions are most probably where the mechanism that produce jets and winds originate. So these regions are really important to understand the feedback process and how the black holes carries information away from this region. And of course, the best way to study these regions in large samples is X-rays. So the plan of the talk is the following. I will focus on two important questions. The first of these questions is, what is the nature and geometry and location of the main X-ray source? This is very important because we as we will see, we don't know much about this X-ray source. We have many open questions regarding it, and understanding its geometry and location can inform us about the powering mechanism. And then we will ask the question, whether the disk always extends down to the innermost stable circular orbit, or whether there are conditions, physical conditions, under which the disk results truncated. And this is really relevant because if we want to measure the spin, we need to get very close to the black hole. So we must be really, so in order to be sensitive to these parameters, we really need to get very close to the black hole. So the plan is I will first explain, trying to convince you why we need to combine spectral and timing information in order to constrain the parameters from these innermost regions. And then I will give an overview of recent results, and then I will discuss how Athena will contribute to this field. Okay, so let's start just giving a look at the basic components that form the X-ray spectrum. So when we look at the X-ray spectrum of a black hole accreting system, what we typically observe is, first of all, a soft component. So this soft component, so if we're looking at an AGN, we call this soft component a soft excess, and we will discuss this component more, but basically we don't know very well the nature of this soft excess. We just know it cannot be direct thermal emission from the disk because these objects are too massive. Or if we are instead looking at a black hole binaries, this soft component is most probably thermal component from the disk. So direct emission from the disk. However, the X-ray spectrum extends up to much higher energies than this soft component. So it can reach up to hundreds of keV. And this, well, but the standard models for accretion do not explain the origin of these components. So to explain this component, we need to invoke the presence of a hot plasma of electrons, Compton pin plasma of electrons that can upscatter the thermal emission coming from the disk. Now, this component is very important because it has been estimated that it can contribute to up to 50% the volumetric power in AGN, and it results to be the dominant X-ray component in the hard state of black hole binaries. Now, however, we don't know much about how it is formed, how it is powered, and what its morphology is. So several morphologies have been proposed, starting from a simple lamppost geometry, then an radially extended region covering the inner parts of the inner accretion of the accretion flow of the accretion disk, or a more vertically extended structure that might be associated with a jet, or a combination of all these. Now, a great way to study this X-ray source is to study its reflected spectrum of the cold material in the accretion disk. Now, the hard X-ray that impinge in the accretion disk, then they get reprocessed. They undergo several processes, and the result is a complex spectrum, as it is shown here, that is made up of several components. We have absorption edges, iron line, lines with the iron line being the most intense of these lines, and then a scattering continuum. Now, this spectrum is highly complex and strongly depends on the properties of the disk, like its density, its ionization profile, even its geometrical properties like the inclination. Well, however, if it is produced in the inner regions of the accretion disk, then we have to factor in also relativistic effects. Now, these relativistic effects what they do is to strongly distort this spectrum. So every emission line is distorted so that it produces a broad red tail. And this makes all the dense lines that are observed in the soft band to blend together. And this process is able to produce a sort of smooth continuum in the soft band. And this smooth soft continuum has been proposed as a possible origin for the observed soft excess in AGN. Now, the shape of this relativistic reflection spectrum also depends on the illumination pattern of the central X-ray source. And these illumination patterns, of course, depend on the geometry of the X-ray source. So by constraining this illumination pattern, we can put constraints on the geometry of the X-ray source. But this spectrum also depends on the distance from the black hole. So we can use these speeds to constrain the innermost stable circular orbit. And since the innermost stable circular orbit of an accretion disk monotonically depend on the spin of the black hole, then we can put constraints on the black hole spin. However, if you look at these plots here, which show the relativistic reflection spectrum as expected for a non-spinning black hole and for a rapidly spinning black hole, you can see that the differences are really subtle. And this basically means that if we want to get good constraints, we need very good data. So the tendency is to average over long exposures or multiple observations to get very good spectra and use them to fit them to relativistic models. However, this approach, I would say it's a bit dangerous, and this is because these sources are highly variable, and the variability that we observe, so the time scale of this variability scales inversely with the black hole mass. So it means that we observe the most rapid variability in smaller black holes, like black hole X-ray binary systems, while when we look at AGN, we typically observe the X-rays to vary on longer time scales. Now, however, this means that on the duration of a typical observation, we might see many variability events, many flares. And this means that by taking time average spectrum, we are getting a static picture of something that is really, it's very dynamic. So it means that in some sense, we might be losing information. For sure, we are losing information, but we also might be getting wrong information. So it is very important to take this variability into account. Now, variability, of course, should have some origin somehow, but in this, for the sake of this talk, we will not discuss possible theories or theories about the origin of this variability. We just use this variability as a tool to study these innermost regions. Now, an important aspect that we must take into account is that the time scales for a given source also depend on the extension and as the distance of the region where variability originates. So this means that if we get, if rapid variability produced far away from the black hole will be smeared out. So we won't observe rapid variability from the outer regions. So when we observe rapid variability, we can be pretty sure it comes from the innermost regions. Now, the obvious way would be to take time-resolved spectra to fit models to the spectra and then see how the parameters of the model change in time. However, this approach is quite limited because to fit very complex models, like, for example, reflection models to a spectrum, we need a lot of counts. And this precludes us to study the shortest variability. So we need other methods. And a good method to study these rapid variabilities is to use spectral timing techniques. Now, spectral timing techniques are based on the Fourier decomposition of light curves. And in this plot here, I show you the power of this approach. So basically, this is a simulated light curve where there is a modulation, sinusoidal modulation, plus noise. Now, if you look at the light curve by eye, you don't see any modulation. It's really difficult to catch this modulation. However, this modulation clearly stands out in the Fourier domain, in the frequency domain. And this is because what we do when we look, when we apply Fourier techniques is to average over different cycles of variability, which has the advantage of smearing out any noise process and enhancing processes that occur on a given time scale. Now, the other advantage is related to what I was saying before, so that rapid variability mostly comes from the innermost regions, while longer timescale variability comes from the outer regions. So when we apply Fourier techniques, what we do is to decompose a light curve into its components, and its variability components simply correspond to variability occurring on different timescales. timescale. So by singling out all these different components, we are singling out emission coming from different distances from the black hole. And then, of course, to have spectral timing, we need to add another dimension, which is energy. Now, this means that by adding the energy dimension, which means extracting light curves in different energy bands dominated by different spectral components, we can study the variability properties of these components and even their correlations. So one obvious application of these techniques is to study the causal connection, the causal relation between spectral components. In particular, we are interested in the response of the accretion disk to irradiation from the X-ray, the hard X-rays from the central compass, from the central source. So this is what we call X-ray reverberation. And to get an idea of what reverberation, X-ray reverberation is, we can simply look at a simple situation of a single flare coming from a very compact source. Now the photons coming out of the source will reach the observer, but a fraction of them will sweep across the accretion disk, and they will be reprocessed at different distances at different times. So the result is that the reprocessed emission will reach the observer with a time delay. This time delay is what we associate to reverberation. So it's what we call X-ray reverberation lag. Now, of course, life is not easy. We don't usually observe single flares. What we observe are complicated stochastic processes that result in a very complicated light curves. So made up of a combination of flares, let's say, on different time scales. So what we expect to see from these light curves, from the reprocessing of these light curves, is a time series that results smoothly out in its most rapid variations and shifted so that the two light curves results, so that a delay is observed between the two light curves. Now, mathematically, this corresponds to convolving the primary light curve with a transfer function. This transfer function or impulse response is what is basically describing the temporal response of the accretion disk to a flash of light. Now, this transfer function is really important because it contains a lot of information about the geometry of the system. Now, to give you an idea, this process is very similar to what is done in reverberation mapping analysis of broadline regions, for example. However, there is a very fundamental differences between these two approaches. In the case of optical UV reverberation of the broadline regions, the irradiating source, so the ionizing source, can be well approximated as a point source. So this makes things a little easier. Instead, in the case of X-ray reverberation, the X-ray source and the reprocessing regions of the disk are so close that we cannot use this approximation anymore. So in the transfer function, the geometry of the X-ray source matters. And here I show you some examples of computed impulse response functions for a compact corona and for a radially extended corona. So as you see, there is a lot of differences that we can constrain using these techniques. Now, in the next part of the talk, I will go through several results that have been obtained, I would say, in the past 10 years or so, that regard the study of X-ray lags in AGN and black hole binaries. Now, before going into the details of these results, I would like to stress the fact that these spectral timing techniques can be used to study any other objects that is variable in principle. And indeed, they have been used to study many other objects, for example, accreting white dwarfs, neutron stars, ultraluminous X-ray sources, tidal disruption events, complex systems of absorbers, and so on and so forth. Okay, so let's start with AGN. There is an obvious reason why we will start with AGN, and the reason is that the first detection of X-ray reverberation has been done by studying an AGN. So basically, this detection came from the study of the causal relation between the soft excess and the power law. So the goal of this study was to understand the origin of the soft excess. And it was done by looking at very good data sets, XMM data set of the source 1H0707, which is an error line CP1. Okay, so this picture here shows the lag amplitude as a function of temporal frequency, which is the inverse of timescales of variability. And this is the typical way how to plot these lags, basically. So basically what has been observed is that on long time scale, which correspond to the shortest temporal frequency, the variability was dominated by these positive lags. Now, these positive lags indicate a time delay of the power law with respect to the soft excess by a few hundreds of seconds, between 100 and 150 in this frequency range. Now, this is not new because these time of lags have been observed for many years, first of all in black hole binaries, and also in many AGN. And there is much discussion about the origin of these hard lags, and the model that so far appears to explain them quite well is a model that assumes fluctuations, propagation of mass accretion rate fluctuation throughout the accretion flow. So we will talk about this a bit more later. Now, the new thing about this was the possibility, thanks to these very good data sets and the fact that the source is highly variable, to look at the highest frequencies that correspond to the shortest time scales of variability. And in this band, what has been observed is a negative lag. Now, a negative lag means that the soft excess is delayed with respect to, so response to the rapid variability coming from the power law from the X-ray source. And this time delay, the measured time delay is of the order of 30 seconds. Now, this time delay is very short, and this is what is being interpreted as a signature of X-ray reverberation. Now, what is interesting is converting these time scales into light crossing time. So if we do this conversion, what we observe is that this time delay corresponds to very short distances in terms in units of gravitational radii. So just a few gravitational radii distance. And the other thing that we observe is that it is observed up to very high frequencies, and this frequency corresponds to variability produced in very compact regions. So of the order of tens of Rg. So this means that what we are observing is the signature of the existence of a compact corona, and we are observing short lags, which means that the disk is likely reaching down close to the black hole, so probably being at the innermost stable circular orbit. Now, many other detections follow this first detection. What we did was to perform a systematic study, systematic search of soft X-ray lags, reverberation lags with XMM. So we looked into the XMM archive. We selected sources that are bright and variable, and we looked into all their archived observations. So we found many more detections of these reverberation lags. And what we found is also a strong correlation between the lag characteristic timescales and the black hole mass. Now, we basically see that these time lags to shift towards higher frequencies for smaller black holes, and their amplitude to decrease for smaller black holes. Now, this is actually expected from from the interpretation that these lags are due to reverberation, because the black hole mass is what regulates the size of the system. So bigger black holes have larger sizes, and so this would produce longer lags. However, if we convert these distances, well, these time delays into light crossing time, gravitational radii light crossing time, we see that they span very small distances of the order of a few gravitational radii. And this is telling us one simple thing, that basically the objects in this sample likely have all the same geometry of the innermost accretion flow. This sample, as I said, I remind you, comprises a variable AGN, bright AGN, that are all radio quiet. And so this means that all these objects probably have a compact corona and the disk extending, down to the innermost stable circular orbit. Now, this study has been recently updated. So new sources have been added to the sample. In particular, these sources are made of small black holes. So it's a sample of low mass black holes. And these samples agree very well with the correlation. So just suggesting that this same mechanism and the same geometry applies to AGN over a wide range of masses, around 4 orders of magnitude in mass. Okay, so far what we have discussed are X-ray reverberation lags that have been observed in the response of the soft excess. So this is really helpful to understand the origin of the soft excess. But what one would expect is also to observe these lags in the iron K line component, which is the most intense line of the reflection spectrum. And indeed, just a few years after the first detection of X-ray reverberation in the soft band, also iron K lags have been observed. These lags have been observed looking at XMM data, but also NuStar data. And Erin Kara performed a systematic study of these lags using also looking at new detections, but also using published iron K lags. And what she found is that iron K lags also follow the same correlation with black hole mass that is observed for soft X-ray reverberation lags. Now, this is telling us basically that the soft excess and the iron K line, so the reflection spectrum, both arise from a very similar close region, if not the same, close to the black hole. So this gives strong support to the idea that the soft excess is due to relativistic reflection. Now, it is really interesting it's interesting to compare these results with other independent results. And one of these results come from microlensing studies. Now, in microlensing studies, what people do is to study the uncorrelated variability in lensed images of distant AGN. And by studying this correlated variability in different energy bands, it is possible to estimate the size of the emitting region. And there is an ongoing effort to measure to make these measurements. And the results show that the X-ray emitting region is as an extension that is of the order of a few 6 Rg or up to about 30 Rg. And as you see, these sizes very well agree with the size scales that we observe from reverberation, that we infer from reverberation. Now, we are now moving, thanks to the addition of new data to the archives, but also to our now ability to design monitoring campaigns that are specifically focused to the detection of reverberation, the study of the reverberation signal. So thanks to these new efforts, it is now possible we are slowly moving beyond a simple detections of reverberation. We are now witnessing more complex phenomena. And one of these is shown here in this slide. Basically, this is a study that has been performed using 16 orbits of XMM, which is a massive campaign that lasted for a total of 2 megaseconds of the narrow line CIFAR-1 IRAS 13224. And for this source, it's been possible to study these legs over each of these observations, and the legs showed in significant variability. Now, what does it mean? It means that the geometry is changing, and it's changing over days time scale, over 1 day time scale. Thanks to, now you can imagine that a measurement of a reverberation lag as its own degeneracies. And that's because the time delay that we measure depends on the black hole mass, it depends on the height of the X-ray source on the disk, and also it depends on the radius where reprocessing occurs. So there is an intrinsic degeneracy. However, by fitting simultaneously all these observations, it was possible to break these degeneracies. And what it has been found is that the height of the X-ray source changes as a function of luminosity. So this highlights the existence, at least in the source, of a dynamic corona. And the study also allowed to well constrain the black hole mass of the source. Another important aspect that has been studied lately has been the possibility that the corona is more structured than we think. So in to first level, these reverberation legs have been interpreted and fitted assuming a compact source, so a point-like source, X-ray source. And this is because basically mathematically this is more simple, and so it helps us to it helps us to draw conclusions, easy conclusion. However, the X-ray might be much more complicated than we think. And indeed, a simple compact source, or point-like source, cannot explain some features that have been observed in several sources. So the first of these features, of course, are hard legs. Now, hard legs can be also visualized in this way. So basically, we can extract leg energy spectra of these legs. So basically, this is done by extracting legs between bands in different energy beams and integrated over a given frequency interval. Now, if we integrate over the frequency interval where hard legs dominate, we see this energy dependence. This energy dependence is telling us that the larger the distance between the energy beams, the longer the leg. Now, propagating fluctuation models can explain this trend, because basically in propagating fluctuation models, we assume that the legs that are produced are due to the travel time, the propagating time from one region of the accretion flow to another inner region of the accretion flow. So it is natural to think that the legs get longer. The legs get longer if these regions are more separated, and so they will also emit a very different spectrum. Now, the problem is that these propagating fluctuation models all assume some radial extension of the X-ray source. So this is in contrast with the idea of a point-like source. And then we have reverberation. Now, this is the leg frequency, the leg energy spectrum, typical of reverberation legs. What is observed in this spectrum is this dip, and this dip, the nature of this dip is uncertain. Actually, this dip is observed in many other sources, so it's quite a common feature. And Wilkins and collaborators show that to explain this dip, one should assume a more complex geometry for the X-ray source. So basically, they assume an radially extended corona, extended out to about 30 Rg to explain the low frequency hard lags. But then in order to explain this dip, they assume that there should be some vertical structure where fluctuation propagates first from outer radii to inner radii and then up to along this structure. Now, even more complications about the idea of a structured corona may come from considering the origin of the soft excess. Now, as I told you, a very good model to explain the origin of the soft excess is the relativistic reflection model. However, there have been so alternatives have been proposed, and one of these, a successful one, is the possibility that the soft excess is produced in a warm atmosphere that sandwiches the inner parts of the accretion disk. Now, this warm optically picked gas would produce a soft excess by Comptonizing the photons from the disk. And actually, this model has been found to well explain the time average spectra of many sources. However, with this model, the problem is that we still haven't explored its temporal properties. In this paper, Gardner and Dunn, actually, the lag that we observe, the reverberation lag, has been fitted, assuming that this is produced via thermalization in a warm corona. However, this needs to be explored further, because in this case, this might mean that the time delays that we measure are not only due to light travel time, but some reprocessing time scale might be significant and relevant for this. So we need to take into account this thermalization time scale too. Now, parallel to studies of X-ray reverberation in AGN are studies of X-ray reverberation in black hole binary instead. So the first detection of an X-ray reverberation lag in a black hole binaries dates back to 2011. It was done by looking at an hard state observation performed with XMM of the source GX39-4. Now, before that, most of the studies, the spectral timing studies of black hole X-ray binaries, were performed using instruments like RXT. So this means that we didn't have access to the soft X-ray band, and the soft X-ray band contains a lot of information because it allows us to observe the disk in the hard state. Now, looking at these lags, what we see is the usual log linear trend that has been observed, that I showed before in AGN, and is typical and can be of these lags and can be well explained in terms of propagating fluctuation models. Now, by extending the analysis in the soft band, it was possible to observe that these lags extend down too, which means that the disk leads this variability, and this variability then propagates through the X-ray emitting region. However, this is what is observed at low frequencies. Going into high frequency, at high frequencies again, in the hard band, we still observe this log linear trend, and we would expect this to extend down to the soft band. However, what is observed in the soft band is an upturn. So this picture here means that some component here is responding to variability in the hard band, and the component we have here is the disk. So this picture has been interpreted in terms of thermal reverberation from the disk. Now, if we measure this lag, the amplitude of this lag, and if we compare it to the soft lags that are observed in AGN, So by extending this correlation down to low masses, what we observe is that this lag is very long. So it's about a factor of 10 longer than expected if a disk reaches down to the innermost stable circular orbit and the corona is compact. However, in a sense, this must not come as a surprise, because as we know, black hole binaries are a complex system. They show complex spectral evolution during outbursts of activity. So this evolution is summarized in this plot. There are plots of hardness, intensity versus intensity. And what we see is that the source goes through this pattern, going through first a hard state and transitioning to a soft state and then going back to the hard state. This evolution is comes with a very strong evolution of the spectral properties of the source. This is like a summary of different spectra from different accretion states. And it also comes with detection with the launch and the possible quenching of a jet. The jet is observed in the hard state, while it is not observed in the soft state. Now, models that try to explain this evolution involve highly truncated accretion disk in the low luminosity hard state and in the quiescent state, which is replaced by an inefficient accretion flow in the inner regions. While for the soft state, these models state that the disk should reach the disk or close to the innermost stable circular orbits, while the Comptonisation region should be more compact and less, contributing less to the overall energy budget. Now, the problem is both theoretical and observational. What happens in between? Because we have a lot of evidence that this is indeed what happens. This is a scenario that could explain that can explain the observation of quiescent state or the low luminosity hard state and of the soft state. But what happens in between is highly debated. In particular, we don't know how the source evolves in the hard state, at what exact phase of the outburst the disk reaches the innermost stable circular orbit, and what happens in the intermediate states, which mark the transition between the hard and the soft state. Of course, this is really important. Understanding these things is really important, because this holds the key to understand the origin of state transition and also to understand how jets are launched and quenched. So what we did was we decided to use reverberation to try and constrain the evolution of the inner flow throughout an outburst. So we looked into the XMM archive, and we could find a bunch of detections of X-ray reverberation. However, these are not a lot of detection, and this is because XMM is not XMM observation of black hole binaries are not very good for this kind of studies. However, with this detection, we could study trends, and what we observe is a trend of decreasing lag amplitude as a function of luminosity. So as the luminosity of the source increases, the lag becomes shorter. Now, this of course calls for a steady change of geometry of the innermost accretion flow throughout the entire hard states. And in particular, this tells us that when the source reaches high luminosities, the light paths between the disk and the X-ray source are shorter than they were at the beginning of the outburst. So this is really consistent with the idea that disk evolves steadily throughout the hard state, with its inner radius moving closer to the black hole and deeper into the X-ray, the Comptonising region. Now, a great improvement in this sense is given by NICER. So a great improvement in the study of reverberation lags. This is because NICER is a very good instrument to perform studies of X-ray reverberation, but it also performs very detailed, accurate monitoring of these sources. So one of the best monitored source, MaxiJ 1820. And this source is also the first one that showed reverberation, for which reverberation was detected with NICER. So Erin Kara showed that this source presents reverberation lags in the bright hard state, and that these reverberation lags obviously evolve as a function of hardness. So they change both in amplitude and in frequency. So we decided to look at these huge data sets and to explore the evolution of these lags throughout the first part of the outburst, from the low luminosity hard state to the transition. So what we observe is that in the first part, so during the hard state, these lags steadily change. So what we observe is that they move to higher frequencies, so their characteristic frequency increases, which means that their intrinsic amplitude decreases as the source moves towards the soft state, so as the source gets softer. Now, what is surprising is what happens near transition. So near transition, this trend breaks, and the lag becomes suddenly longer. Now, this can be better seen in this kind of plots. So these are the typical lag frequency spectrum that we observe in the hard state. So we see a hard lag and then a soft lag that changes with hardness. And then in the hard soft transition, things change completely. We do not observe the hard lag anymore, but we observe a long lag, which is about 10 times longer than the reverberation lag observed in the hard state. Now, this was also observed independently by Wang and collaborators. And more recently, the same group performed systematic studies of sources observed by NICER, and they found that this behavior of lag amplitude increasing at transition by about 1 order of magnitude is a common property of black hole binaries. However, to understand the origin of these...
Barbara, you have 5 minutes.
Okay, to understand the origin of this behavior, MaxiJ 1820 is the best source because it has very detailed radio monitoring, and in the radio the source shows a sudden flare. This flare is very typical of black hole binaries in the radio band, and it is usually accompanied by ejection of discrete jet knots that propagate at a speed close to the speed of light. Now, if we observe the detection of reverberation lags, of a long reverberation lag in this plot, we see that we start seeing a long reverberation lag about 3 to 4 days before this ejection. Now, a long reverberation lag means that either the corona is expanding or is sort of ejected, so it is observed at higher, it is farther away from the disk, so this would produce long lags. So in a sense, this can be, this might mean that this event that characterize the reverberation lag before transition are the precursors of this discrete jet ejection, and this gives a strong support to the idea that the jet and the corona are connected at transition. Now, this idea is not new. A corona-jet connection was invoked several times in the past, in particular to explain several other timing properties. For example, the hard lags versus gamma correlation with spectral index correlation, or the long-term trends observed recently in GRS 1915. Now, another obvious question is what happens to the disk. Now, using the spectral timing techniques, what we did was to map the changes in temperature of the reverberating part of the accretion disk. And what we found is that this temperature steadily increases as the source becomes softer, so as the source moves towards the soft state. Now, this can be interpreted as in line with a scenario where the inner radius of the disk steadily decreases, reaching the innermost, close to the innermost stable circular orbit right at transition. This trend is consistent also with the behavior, with the evolution of type C QPOs that are usually explained in terms of a progressively less truncated disk. However, this is not the only proposed scenario for this data set. Another scenario has been proposed based mostly on the evolution of broad iron lines in this source. And this scenario invokes a vertically contracting corona. However, we must note that recent results from IXP, so from X-ray polarimetry, suggest that the X-ray source is more radially extended on the plane of the disk in the hard state. Now, another important aspect that needs to be acknowledged is the development of spectral timing models. So we need this model to constrain physical parameters. Now, we have a lot of advancement in this field lately. So we are building up more models. Some of them have fancy names, others have no names. And these models must account for GR, for the properties of the disk, for the different coronal geometries. They must self-consistently account for hard lags, and they must simultaneously fit time average spectra and spectral timing properties. This is necessary to break the generacies. So as you might imagine, this needs a lot of efforts, and there are fortunately many groups that are putting this effort into building these models. Now let's give a final look of how Athena will help us with these measurements. Now, so the first thing we have to consider is how the sensitivity of lag measurements depends on the source parameters and on the observation. So basically, what we observe is two main regimes for AGN and black hole binaries, but basically what we observe is that the error on the lag decreases inversely with the count rate. So basically, brighter sources will give smaller error on the lags. Now, the error on the lags also depends, and the sensitivity also depends on the exposure time. So basically, up to now, the main way to address this problem was to try and detect the reverberation lags, was to stare at the sources for longer time and to select the brightest sources. So this allowed us to get the highest signal to noise possible and to help us with these measurements. However, this also means that large area detectors will really help us to exploit these techniques at its best. So for large area detectors, we'll have a great improvement in lag sensitivity. Now, however, there is a caveat, and the caveat is that these sources can get very bright. So like black hole binaries can get very bright. The transition between the hard to the soft state. And so we also need to manage problems like pileup in order to be able to observe them in these important phases of the outburst. Now, this means so if we factor in all these information, what we expect with Athena is a factor of 3 increase in the detection, in the sensitivity of soft reverberation lags detection, and a factor about 1.4 for iron K lags. So what we would expect, first of all, is a huge increase in the number of detections, so a factor at least 3 more, And this will allow us to study reverberation possibly in different AGN classes, and possibly to look at reverberation in black hole binaries over different states. Now, these are a simulation. This is a simulation of the Athena WFI. So this is a 500 kilosecond observation that's recovering the exposure time of XMM for this source. So the shaded area is the XMM observation. And so what we see here is that we will be able to look. So we will be very sensitive to the high frequencies. So at high frequency, so we will be able to map delays that are of the order of 1 RG like crossing time. And we will be sensitive to structures transfer function. Now, detecting these structures in the transfer function is very important, because actually models predict a lot of structure in the high frequency band. And this will allow us to distinguish between possible geometries. This is an example to show you the importance of the high frequencies. So these are two transfer functions that have been adapted so as to match at intermediate and low frequencies. So this is the frequency band where we are usually sensitive with XMM. However, the real difference is observed at high frequency. So looking at structures in this frequency band, we will be able to distinguish between different models. So now this is, so this is important also to distinguish different coronal geometry, because, for example, this is illustrated in this example here. So this shows the transfer function expected for a compact corona and for an extended corona. Now, as you see, the resulting lag will have similar shape at low and intermediate frequencies, but again, they will predict different structures at high frequencies. And indeed, simulations with Athena show that we will be very sensitive to this high frequency, to differences between the predicted lags in this frequency range. Now, another point is to our ability to constrain the black hole spin. So to constrain the black hole spin, we need to be sensitive to very short lags. And this is an Athena simulation that shows that we will actually be able to constrain the black hole spin using reverberation. And in shaded area, the shaded area is the 1 sigma epic PN. So as you see, it is almost impossible to constrain the black hole spin using epic PN data, but it will be possible with Athena. And another important point is the possibility to observe iron K reverberation. So as you know, there will be a huge improvement in the effective area in the soft band, but the improvement will be modest in the iron K band. So this means that in order to study iron K reverberation, we will need to focus on the brightest sources and most variable sources. However, this is not a problem, because the great advantage will be that by using broadband lag energy spectrum, so fitting broadband models of lag spectra, we will be able to constrain many different scenarios. And of course, we will also take advantage of the unprecedented spectral resolution of this data. Okay, so in conclusion, we saw that X-ray reverberation is an independent and powerful method to study the innermost regions of the black hole accreting system. We saw how XMM Newton and NICER help us to really move forward in the study of X-ray reverberation. But of course, we need better data to go beyond simple measurements, and this will also allow us to perform more detailed modeling and to perform more complex studies of the dynamics of this system, of the X-ray source and the disk. And Athena will be great for this because it will provide a large effective area unprecedented spectral resolution, good timing capabilities, and a broadband energy coverage. So in summary, my conclusion is let's build Athena. Thank you.
Thank you very much, Barbara. For everybody. Thanks a lot for this very comprehensive and updates on spectral timing capabilities for black holes on different scales. I see some questions. Let me no, it disappeared. Well, I don't know if Sylvia just gave. Yes, now it's here. Panayotis, yes, I think you can talk. Just go ahead. Yes? Panayotis, can you speak? You're permitted if you have a question. Yes? No? No, if you want to write it in the chat in the meantime, I can then read it for you. Okay, any other questions? Yes, Elisa.
Hi, thanks a lot for the talk. Very, very interesting. I was wondering in this, all time lag analysis, are the outflowing winds only a secondary effect or not? So yeah, I would like to know if they can influence in any way, your results.
Okay, so in principle, they should not, because we expect the timescale to be longer. However, so there are studies that have been performed to show that actually, so this outflowing wind might produce, for example, soft lags that are due to recombination time. And in sources like NGC 4051, we do not expect these lags to affect the high frequency regime where we observe the reverberation lags. However, they are a really important ingredient. I didn't talk about them. I didn't account for them in simulations, but they're really important because they might have a great influence, most of all on the hard lags. And the hard lags, depending on how we model them, influence our constraints on the soft lags, so on the reverberation lags. So aside from this, aside from the taking care of them for properly constraining reverberation lags, we can also use spectral timing techniques to infer the properties of these winds, because these winds might vary on quite short time scales. So we might very well use these techniques to constrain, for example, their density, and so their launch region, so on and so forth. So they are really, really important ingredients.
Thanks.
Thank you. We have another question from Massimo. Go ahead.
Yeah, thank you, Barbara, for the interesting, nice, and complete review on the subject, and it's very useful. I have actually a comment and a question. The general comment is maybe somewhat linked to Elisa's question. I think, okay, you show simulation with Athena, but I think you concentrate in, say, probing the way you structure these simulations. You probably say optimize the way you may constrain continuum or say broad feature in your spectra. Mm-hmm. I think applying these similar, I was wondering if applying similar simulations to XIFU data and making the best, optimizing for the high energy resolution of, and maybe selecting frequencies and energy beams depending on the line emission or absorption line width you expect on different time scales. So going from so low frequency to high frequencies, you would expect your line features in lags to broaden, or lag spectra to broaden, or being narrower on longer time scales. And this type of information, I was wondering, so if you tried some simulations, making the best, optimizing for also the energy resolution. This is my comment. But and my question is actually curiosity. If sometimes the corona and disk system is that we think is valid for binaries and AGN, we take as analogy on the sun. And the sun, the corona, solar corona, and the sun surface are by analogy similar geometry, similar. So you have a magnetic reconnection, ejecta, coronal mass ejecta on top of your solar surface. And I was wondering if lag spectra and analyses similar to the one you have shown have been ever applied to data from the sun, and if you get similar results.
I don't know. I don't know, but it's an interesting point. I should look into it. So no, my reply to this question is I don't know. For the first comment, I didn't actually try to simulate X-high-few like timing view of an obscure or an absorber or a wind, but there are groups that are working on that, and I must say that high spectral resolution makes the difference, because, for example, what one might expect is a drop in the fraction of linearly correlated variability when you have an absorber on your line of sight. And if so, in principle, you should see. So what we usually see what we usually measure to compute to measure the amount of linear variability is a coherent spectra. So we basically measure the fraction of linearly correlated variability as a function of energy. Now, it would be possible with high resolution to see these drops of coherence on finer scales. So at the line at the scales, at the energy scales of the line. So this would be really helpful to constrain models of absorbers using spectral timing.
Thank you.
Okay, we have maybe the Panayotis. He just sent in Q&A question if you want to comment. So what he says is that the Zogby 2019 paper finds that the iron K emission is actually not broad, and reverberation might result actually due to absorption rather. So, and he puts up two cases, NGC 4151 and 1365, where this might be the case. So I don't know if you want to comment on this.
Yes, so yes, that's true. That was revised. When that result was revised after looking at more detailed data that show complex absorption. Well, I don't have specific comments about that. We know that two sources may not be fully explained by reverberation, but we have a lot more sources showing this signal. And we also have this signal detected in black hole binaries, where we don't have these complex systems of absorbers. So the idea, so basically, we are quite confident that reverberation is there and shows all these scaling properties that we observe.
Okay, thanks a lot. Are there any last fast question? No, I don't see so. If not, let's thank again Barbara for the very nice talk. Thanks a lot. And I just remind you that in November, we will not do the webinars because we will have the meeting in Barcelona, the Athena meeting, between the 7th and the 10th of November. And then the next one will be December 14, where the speaker will be Yona Saradaki, Mineralogy of Interstellar Dust and X-ray Overview. So thank you very much. And hopefully see you either at the meeting in November or the 14th of December for the webinar. Thanks a lot. Thank you, Barbara, again.